Software Engineering Radio episode 100, Software in Space.
This is Software Engineering Radio, the podcast for professional developers, on the web at se-radio.net. SE Radio brings you relevant and detailed discussions and interviews on software engineering topics every 10 days. Thanks to our audience and the partners listed on our website for supporting the podcast.
Welcome, listeners, to this birthday episode of SE Radio. This is episode 100. So this episode is about software in space. We talked to Hans-Joachim Popp from the DLR, Germany, Deutsche Forschungsanstalt für Luft- und Raumfahrt, kind of the German NASA somehow, in some way. Anyway, but before we get started, I really want to say a couple of words about SE Radio and how it has developed. As I said, this is episode 100. We have been doing this for 2.5 years now. During that time, I think it's fair to say that we've become one of the premier podcasts on software engineering. Thanks to all of you for listening. We have way more than 10,000 listeners per episode, which is really great. The exact numbers are, of course, always a little bit fuzzy. So, anyway, suffice to say we have way more than 10,000. We're talking to interesting folks because SE Radio has become, well, people know it to some extent. People are willing to talk to us. So that's great. That helps make it even more interesting in the future. We also organized, or are probably, hopefully organizing the get-together this autumn. We still need more papers. We need more people writing position papers to come. If we look at the current numbers, we don't have enough people to actually run the thing. So we need more. Otherwise, we have to cancel it, unfortunately. A couple of other things that I want to mention, upcoming changes in SE Radio. One thing is that we will have transcripts for all the episodes. We already have 2 or 3 transcripts online. I think it's episodes 88 and 87, if I'm not mistaken. The transcripts are made possible, brought to you by Itemis, a German consulting company, itemis.de or itemis.eu if you're English speaking. And Michael Manulis helps us get these things organized. He's a listener who has volunteered to help with getting the transcripts done and doing quality assurance and stuff. This is also a call for help to all of you listeners. Currently, I do most of the work, and it's getting too much for me. I have to step down. I have to do less work for SE Radio. I can't continue like that. It's really too much work. It takes away a lot from all kinds of other activities, among them earning money. If you want to help with SE Radio, for example, writing show notes, organizing links for topics, putting up the podcasts, uploading them and editing the page, making sure the people who do the actual interviews send in their audio in time, all that stuff. The to some extent the grunt work of keeping the website running, of making sure we have a new podcast every 10 days and all that stuff. I would really, really, really appreciate your help. So if somebody was willing to help us there, of course you'll be part of the SE Radio team. Please let us know. We really appreciate that. As I said, I have to step down a little bit and do less work. I really like doing the interviews and stuff, and that's true for all of the others in the team. But we need to get help doing the work part of it, which is keeping the stuff running. So please, if you're able to help, please contact the team at team@seradio.net and help us out. I think that's it. Let's now get started with the actual episode, with the actual content. As I said, it's about software in space with Hans-Joachim Popp from DLR. This is another episode recorded at OOP, and today we are talking to Hans-Joachim Popp from DLR. You probably will not know what that is, so welcome. And why don't you tell our listeners a little bit about you and what DLR is and what they do, and so they know what it's all about today.
About myself, I come from the engineering side. I am electrical engineer specializing in control science, and very early I went into the real-time processing business, and from there I did my PhD in software ergonomics or software or human factors, as it's called in the US, and on the other hand, software engineering methods, specializing in the application environment of hospitals, and they're again specializing in intensive care units. So where you have high risks, where you can't train people doing their business with the computers. That was my special theme in my PhD, and from there moved into the industry, into development of high risk software or software for high risk environments. And from there I went into the general IT environment, became the CIO, the Chief Information Officer of one of the biggest certifiers in Germany, the TÜV, Southern Germany, TÜV Süddeutschland, as it's called, and became a responsible person for the delivery of the whole IT business of TÜV. And now, since beginning of 2005, I am the CIO of the German Aerospace Center. In German, it's called Deutsches Zentrum für Luft- und Raumfahrt. That's why the abbreviation. So we are, you can say, a very basic development partner of the German and the European aircraft and spacecraft industry. That's our core business, and then we have in travel, in the travel industry, in the vehicle industry, and also in the energy industry, our partners.
So the topic today is software quality for mission-critical space systems. And of course, some of you know that I'm a pilot and an airplane and space nut, so I'm of course very happy to have the opportunity to talk about that stuff. So we're basing this basically on your presentation at OP. So let's start with a little history of software in space. You have a couple of nice examples of how this stuff evolved. So why don't you give our audience somewhat of a history of all that stuff?
I want to start out from the beginning, where software started to play a major role in the construction of spacecrafts. That you can say it began with Mariner 4 in 1964, where the first programmed or kind of software-based system was installed, and then from there it began a cultural change in the minds of the developer, you can say, because it took several years until they really got aware of the importance of software. They started out looking into hardware faults, all kinds of redundancy, but always hardware redundancies. Nobody came to the conclusion that it could also be a good idea to have redundant development teams, redundant languages and all that. So it took a long time and several catastrophes to find that out. And in my talk, I have some very old slides from for us in Germany. I would say the crash of the Ariane 5, the maiden flight of Ariane 5 was the major point where the German software developers in the spacecraft industry began to introduce quality assurance in software development. That's the major point. As most of you might know, the Ariane 5 crashed just because of some a missing casting, so it was just overflows that were occurring, and that was a disaster that had cost about 1 billion euros, and only some lines of code could have rescued that. So this was really a change in the minds, and that was the beginning of the foundation of quality assurance circles, work groups, really dealing with that.
So in which language was the Ariane 5 code written?
That was a good language, Ada,
okay.
but if you, it doesn't help as long as you write code. That's that was Ada, and at that time most of the code for these really mission critical software was written in Ada.
Yeah, you have a couple of other examples of well-known disasters.
Yes.
How were they same problem, basically a coding flaw, or what are the typical reasons for disasters? You have the A320 crash in Mühlhausen.
Yes.
So what are some of the other reasons why things go wrong?
Well, what I wanted to point out is that more and more the disasters later had not only programming flaws as a basis, but also severe faults in the requirements engineering, in the analysis of the whole system. As an ergonomics person, I would say there were system ergonomic faults. That means you have not only a technical system, but you have a human in the system, and all this together.
Right.
There came the faults where the pilot lost or got lost in the very complicated procedures during critical situations. And then the A320 crash is one example where the manufacturer can obviously say the pilot is in charge of that disaster. But if you look into the diagrams and the very complicated gears working together, software side and hardware side, then you can say it's easy to get lost in that.
Yeah, we're recording this in January, not too long after the BA-38 crash. I think it was the 777 in Heathrow, where people say that both engines were lost on short final, which also doesn't look like pilot error only. So there also might lurk some software problem there.
It sounds funny, and we will see what comes out.
Yeah,
there.
we shouldn't be too early to say something, but anyway. There is also something about the Mars Climate Orbiter. I actually wasn't aware that there was some problem with it. So what was going on there?
The Climate Orbiter was supposed to swing into an orbit around the Mars, but there were calculation errors, and the curve or the orbit curve was not calculated properly. So it didn't go into a proper orbit, but crashed on the surface of the Mars. And this was only because the calculation units were mixed. So one team was calculating in yards per pound and per second, and the others were in metrics. And this would be no surprise if the teams would have been in different countries, but they were both in US. So this is the difference. So, funny, but again, it was due to missing testing environments, missing testing procedures. And what we do today is we always take out hardware pieces and simulate them by software one by one. And so at the end, we have the complete system in software and in hardware. Right. So we have a better chance to find these flaws.
So let's go from, let's say, motivation through the disasters to some of the solutions. Let's look at software engineering in mission critical systems, what you do there. So you have two case studies here.
Yes.
It's called Vertis, whatever that is.
Vertis is an instrument that is now, as we're speaking, orbiting the Venus and trying to find out something about the atmosphere of the Venus. And one of our teams did the software integration for these infrared cameras, and this was for us a major step in developing high-risk software. And that's why I have this as a little example. I have also some slides on how the hardware looks. It's not very different from what we know
So is this off-the-shelf hardware or is this custom-made?
No. This is all certified hardware because we have radiation, we have high temperatures, we have very low temperatures. So you have all kinds. You need everything is in pure gold at minimum. But yes, you have better metals than gold for that in the meantime. But it's all certified hardware, of course.
And
still, it's not the major part of the costs, of course, to have that hardware.
So how much processing power is there? Is it like a 386, 486, or how much memory? Do you have any feel for that?
Well, in general, you can calculate that. I would estimate that we are in the hardware which is used here. You can say maybe we are 10 years back from what we have now on top. So it's very conservative, and processors are always much slower. But also energy consumption is a big thing. So we are calculating, or the rate is much lower to save energy, and compared to our top computers we have, of course, they are slow.
Yeah, there's always this joke. There is today more computing power on your mobile phone than what they had when they flew to the moon.
Yes, much more. Anyway, what is interesting is that these projects are done by teams that are mixed by different coming from different European countries. So you not only have the different languages, but of course you have different cultures and all that. So if you want to have some functioning software in the end, you have to apply really strict metrics and strict methods of cooperation.
So do you use things like UML or something, or do you have your own methods?
There is in this case we used UML. We used the ROSE environment for that, and I come to that a little later in detail. But the hardware, from the functional point of view, is quite what we know from everyday computer hardware. It's better material, of course. It's conservative, it's slower, it has less memory, but basically, and this is also a project that has been done in C. So, and a part of it is assembler, but most of it is in C, in pure C.
And any subset like MISRA that the people use in automotive, or is it full C with all the pointer matching and stuff?
It is just plain C, but of course the methods we used and the testing environment restricts the use of different instructions, of certain instructions, of course. The method is a kind of a VModel. The standard VModel, it has some more steps in between you usually don't have, but we are really focusing on requirements engineering, and in the course of development we had most of the problems came from missing requirements or states we didn't describe in our
state machine base.
The states in the state machine that were not described. That was a major error source.
So can you give our listeners a little introduction to the VModel and what you changed there? I guess they're more familiar with XP and other agile processes, so they probably don't know much about this stuff. So.
Well, it's the VModel. Of course, most of you will know that you always have some requirements paper, or you have a design paper, and you evaluate that, you validate that against as certified results that come out of the coding. And of course you can granulate this a little more. Usually you just have the paperwork on the requirement definition and the architecture, and there we have two more steps. We have after the architectural design, we have a detailed design phase where we do on a very low level units testing against a detailed design study. So it's more granular, but it's basically a VModel as you know it.
Okay.
I just wanted to point out that, of course, in today's missions, we start a mission before we have reached the end of the development, because it might take years to finalize software, and we start the mission as soon as we have the basic software in place. So
you mean
we are able
launch?
Yes, launch. Yes.
Oh, cool. You mean what you're saying is, as the spacecraft's already on its way to wherever it's going, you update the software.
We still calculate that we have to do development work, and we calculate that we can learn on the way. Like on the way, if you have a 4 years mission, then at the end you will of course have several updates of even core units of the software in place. And in the history, well, if you go back again to the Voyager missions, then if you wouldn't have had the chance to update, then this Voyager wouldn't be as active as it is today. And as we speak here, 30 years after launch, it's still this craft is still speaking to us.
I think it's recently left the solar system, right?
Yes, right. In August, it left the solar system and has again given us some proofs of special astronomic things. So it's incredible how long this spacecraft is on its way, and this couldn't be without severe changes in the coding, of course.
Do you know what the languages were that have been used back then for Voyager?
Well, that's all assembler.
Okay.
And I know that the Voyager, as far as I know, it's about 4,000 instructions you can place there. And it has a tape recorder to store data, because the memory all together is only 4K. Yeah. And so you need it for program and for result data. And of course, the images Voyager took were much bigger. So they were stored on separate tape recorders and sent then back to Earth.
Flying museum, I guess.
Yes. Fascinating.
Yeah. So before we get to the metrics and some of the process and review stuff you're doing, just give me some overview about which languages and operating systems and other tools you use. Is it still, as you said, mainly C? Does Ada still play a role?
I can only talk for the research side, and there we use mainly C. We use, as operating systems, of course, we have specialized operating systems for real-time use that are that have been used for many years, that are proven. Of course, we don't change to Windows X, Y, Z.
Well, sure. But maybe you could use Lynx OS or whatever these off-the-shelf real-time systems are. So you don't do this. You have your own operating system.
There is big experiences. Most of the things, most of the operating systems have a long history, and they are not changed very often.
Yeah. And before you mentioned that you use a lot of UML modeling, do you also use code generation, or do you code everything manually?
We don't use code generation for obvious reasons, because you don't want to maximize risks. We try to reduce the lines of code. For this mission I just mentioned, it's only 20,000 lines of code, so a very, very small amount, but we invested for each line we invested about half an hour at least
review time or development time. I also somewhere saw the ratio between application code and test code, and I think it was 12:1.
Yeah, 12:1. Yes. Yeah, that's also an important thing. I told you that we try to replace hardware pieces by software. Hardware in the loop testing, and of course this takes a lot of coding or scaffolding around that. So it sounds scary, but I think it's quite normal that if you have such a high risk code, even if it's a small code, you need a lot of things around it.
Yeah.
So.
Yeah. Okay, so in addition to coding, you already mentioned you do a lot of paperwork, specs and reviews. So can you elaborate a little bit on the practices you have there?
Well, we do several kinds of automatic code reviews. So where we try to automatically test the code with respect to certain common flaws or design errors.
Yeah.
But in the end, we review the code regularly in teams where we look into the code. We try to explain, the developer tries to explain the code to some person who is not involved, who learns or reviews the code. With the developer usually is the junior developer, and the senior developer is looking into the code and asks questions.
Okay.
Which can be very exhausting for the developer.
Yes,
but it helps. It helps very much, and you can find much more of the errors if you do it that way. It's very expensive, time consuming.
Yeah.
But it brings us to a very high level of or low level of errors in total.
Yeah.
I know that from our work in the hospital environment also, where this is done regularly and leads to really a very high quality.
But I guess it can be a challenge for the ego of the programmer if their code is basically... So there needs to be a really working team, so they accept criticism from others.
The first thing you have to do is to establish a culture of being free to do errors. Yeah.
Yep.
That you don't ask why did you do that or
stupid idea,
but where people can feel free to talk about their problems. And of course, yes, this is a you can't use that in a hierarchical environment as you have it maybe in other industries where high pressure is in place. You need the freedom to make faults and to find them and to talk about them. And many catastrophes occurred because this didn't function. Because most of the errors were known, were even discussed on the lower level, but the management closed their eyes and said, well, I don't want to hear it. And for us, this is really a cultural thing, a prerequisite.
Are there any other tools you think are worthwhile mentioning? How do you specify requirements? Is it basically you write a Word document, or do you do anything more?
Well, we have a special tool for, at least for this mission, and we try to establish that's Requisite Pro, where we do the requirements engineering. There are several other tools, but this our standard environment we use for high risk developments contains that, and for code verification we use this very good but also very expensive tool, Polyspace, and of course, configuration management plays a major role, and there we used the clear case, and so there's a whole bunch of tools we try to establish in DLR for company-wide use.
I guess you also, to measure quality and problems and issues, you probably do a couple of metrics, I would guess. So can you say something about the kinds of metrics you use?
We, of course, try to measure how many faults we program, how many errors we find per day or during the development, and of course the reasons, where do they come from and where do we have to focus on. And interesting is that we really how we divide our development time. The pure development is only 40% of the time. 25% we invested into management, into systems engineering. That's the view from really above, where you look into the technical things and the humans or the operators. and 35% we invest into the design. So not touching any keyboard, but just thinking about how to things and the integration tests. And of course, we try to measure productivity. And there we found out that we, having this high level of quality, we can produce 0.6 lines of code per hour in the development. Of course, this is a very small project.
Do you want to say maybe something, so we're actually nearing the end because you're somewhat in a hurry, you have to do the talk. What kind of errors you can find using the static analysis and coverage tools? How do you distinguish between what you do in reviews and what you do with automated tools?
Well, of course, the coverage tools can only find a small set of errors, and most of the errors still are on the requirements level or on the semantic level, and we use them. We use the code coverage tools, but it's not sufficient. You still have to review the whole system and to have a test environment where you, as I said, where you test the whole system together, the integration tests, where you play the whole mission through and see what happens. So it's not enough to have the static code analysis.
Okay. And one last thing that I'm interested in is this redundancy stuff. Obviously, you have probably redundant hardware.
Sure.
And also you try to get rid of those accidental errors by not using the same hardware in the two redundant cases. You have different processors, I guess.
Yes.
Do you also do redundancy in software? Do you do like one software in C, the other one in Ada or assembly language to make sure the compiler doesn't kill you?
There are parts that are in different languages, but I think even more important is that you have different minds involved, different teams. One person who is not that deep into that spec is really looking into the specification, coming from outside, posing questions that are just posed with a view from outside the project. And there you find, I think, the major flaws. Of course, it would be good to have software parts written in different languages that control each other. This is done partially, but of course, it's a matter of skills and in the end costs that you can have different developers team. What in medicine, of course, that is done regularly.
I also heard that in Airbus in the flight control software they do it. Ada and C, I think, or C++. So to wrap this up, why don't you give us your summary, your lessons learned from the kinds of projects, and hope that the people who don't necessarily work on these kinds of things take something away from that?
I have a mission in my company to establish a software engineering methodology that is used by all of our developers. That's the dream. And why can I dream of that? Because we are spending 100 million euros a year for software development. So there is a good reason to introduce that. And of course, you always have the question, why should we invest in that? Because it costs too much, and it's always a problem to convince people that it's not more money, but you can save money in the end. But this is one of my missions, and of course I try to remind people that we have in these high risk missions, we have to go forward conservatively in slow steps. And we have this cultural thing that the project manager has to be open for any remark from the developer where they say we don't feel good with this and this, or we have a problem, we see a problem there. It has to be open and grab this problem and say, let's go into detail what's happening there, because it's gonna come back in the end, and this is one of this means you have to accept each other in a team, and everybody is free to make an error, and to report it.
So once again, it's a people problem.
Yes.
Okay. So thank you
Just
very
like always.
Yeah. Nothing different. Same old thing.
Yeah.
So thank you very much for being on the show. I appreciate it.
Thank you.
Thanks for listening to Software Engineering Radio. If you want more information about the podcast and all the other episodes, visit our website at se-radio.net. If you want to support us, you can donate to the SE Radio team via the website, or you can advertise for SE Radio, for example, by clicking on the Dig, Reddit, Delicious and Slashdot buttons. To contact the team, please send email to team@seradio.net, or if it's specific to an episode, please use the comments facility on the website so other people can read and react to your comments. This episode of Software Engineering Radio, as well as all other episodes, are licensed under a Creative Commons license. Please see the website for details. Thanks to Charlie Crow and the PodSafe Music Network for the music used in this show. The song is called Vegas Hard Rock Shuffle.